start recording, and then let me go ahead and mirror this again. Okay, so let's think about the data structures that we've already encountered. So let's just maybe do a quick little review. What data structures have we already encountered? Just throw some out. Okay, so we have a linked list. What else? Okay, the binary search tree. And again, both of those were using pointers. The most basic one, what was the first one we started with? Starts with an A, ends with an A. Array. Hooray, you guys got it. So these are the ones we've looked at already, and you can really say things like if we were to look at each of these, we can go ahead and talk about, like, for example, what is the cost to access a linked list or a binary search tree? Let's just do a couple quick review problems. Linked lists, we'll do that in the order we wrote. What was the cost to access an element, big O? What was it? Is linear. So remember, you have to, in worst case, you have to iterate through the entire list. A binary search tree, of course, that we had bigger nodes with the binary search tree, but what was the access for a binary search tree? We were able to get back to a binary search, so it was big O of, what was it? Yeah, you're back to a logarithmic time access. And what about for an array? This was really nice. What was the access time for an array? It was a constant. Remember, your array, everything is contiguous in memory, so you could immediately, just by looking at the access index, go exactly to that spot in memory. So that's going to be a constant time. It did not depend on the actual length of the list. We also talked things about insertion, and if we were to look at a linked list, what was the cost to insert into a linked list? Think about it. Don't just review, think about this. Linked list. All you have to do is create a node and make that your head. It's in the list now. So if doesn't matter how long the list is, if you're going to just put it right, so you have a linked list. So let's just think about that. You have a linked list. And so on, and you want some new node right here at the beginning. Just put it there. Doesn't matter how long that list was if you're an insert right at the beginning. No. So therefore, you could think that it was big O of 1. The length of the list did not affect how long it took you to insert something. So, binary search tree. If you think about it, each time you were able to cut the problem in half by just using the quick comparison, so it was also logarithmic. And to insert to an array, the worst case was you maybe have to move the whole array because you didn't allocate enough space up front. So what was the insertion for for an array? How much time did that take? Order of magnitude, that was linear. You would have to copy every element. So again, these are the ones we've already looked at. We're going to look at a few more today. The ones we're going to look at today, of course, this first slide kind of spoils it. There's going to be a hash table. There's going to be tries. So these are going to be an amalgamation of the ones that we've done earlier, just like you kind of saw that a binary search tree was just a more advanced linked list where you had the comparison. These two are actually going to be an amalgamation of linked list and arrays. So let's go ahead and see how they work out and see what their access, insertion, and we also talked about search as well. Let's also just throw this up here. So let's move this linked list over. To search a linked list, does anyone remember? Yes, n, because you have to go through each, you have to traverse the whole list. For the binary search tree, well, it's basically you'll just cut the problem in half each time by the construction of it. So it'll again be log of n, and of course, searching an array. Well, this one's a little bit tricky. If it's not sorted. Let's say, so there's two scenarios. If the array is not sorted, what would it be? Nope. If it's not, okay, it is n, but there, no, let's think about that. Yeah, okay, yeah, we can go that. So I guess I was thinking about this different way. So if it's unsorted, so it's not sorted, it is going to be big O of n. And if it is sorted, what would it be? It would not be constant. It would not be linear. Somewhere in between there. Logarithmic. Why? What algorithm what have we been working with that allows you to search in logarithmic time? Your bisection or binary search. And I guess what I was thinking, the reason I hesitated, Kenneth, is because if it's not sorted and you wanted to sort it, you can do n log n merge sort, and then you can go ahead and do the binary search. So it would be n log n plus log n, but then you could also think about like if you were doing big O of n log n to sort during using a merge search plus big O of log n to then do your bisection search. But what do you know about, again, this is all good reviews for the final and things. These are kind of the types of questions that could show up. What is big O of n log n plus big O of log n?
Big O of n log n.
Do you agree, Anna?
No. Wait, wouldn't it just be big O of n?
What's the larger one? N log n is larger.
Than linear?
It would be, let's write it. It would be big O of n log n, because remember that n log n times n is going to be larger than this. So this is the dominant term. So again, something to review over the next few weeks as we get ready to the final. So let's hash this out. Hash tables. So to start with a hash table, what we're going to do is start with an array. And I just wrote the array vertically, as everything will play out later. But a hash table is a data structure that allows us to associate keys with values. What data structure have we already encountered in Python that kind of has a key value pairing? Dictionary. So again, as opposed to Bailey, I feel like I'm always looking over there, so just shout loud in my right ear, and then I'll listen over here as well. So again, this is a hash table is a dictionary in Python is implemented using a hash table. So we do already have this idea of key value pairs. So it looks like an array where we can jump to each location in its index. So again, if we could jump to each location by its index, does anyone remember what we called this? This was called blank access. We have random access. So we are able to go in anywhere just using its index. So what we'll then go ahead and do, you can see right here, I labeled this on the next slide, how many boxes there are. There are going to be 25 boxes plus the 0, so 26 boxes. So let's suppose we want to go ahead and index, or let's suppose we want to go ahead and make a hash table for names. So a way a hash table is going to work is we're going to have essentially 26 buckets, one for each letter of the alphabet right here. And again, we don't have to have 26. Maybe we're hashing, maybe we're looking at numbers. And if we're looking at numbers, how many buckets would there be? How many digits are there in our number system? And 0, so that would be 10 buckets. So again, you don't have to have exactly 26 buckets. You may have 10. It all depends on the problem right there. And we're going to see what this approach does to the access time, the search time, and the insertion time for various things. So here's our 26 buckets. And let's say we're wanting to go ahead and put names in these buckets. So let's go ahead and do something a little bit magical here with Mr. Albus. So Albus, we'll go ahead and consider his name starts with A. So let's go ahead and put him in the first bucket. And then what we'll do is, let's say we have another name, Zacharias. Of course, he would go in the 26 bucket right there. So we can go ahead and continue in this process. Say we have Hermione right here. That would, of course, go, and I think that's the 7th bucket. Yeah, 7th is letter. So you can see right here where we're putting each of these buckets. And maybe this kind of this notation is maybe getting you to think of like what we're actually going to be doing. So if we continued in this pattern, here we have a couple more names. We have Cedric, Draco, Fred, Ginny, Hermione, James, Kingsley. By the way, I don't know if anyone has, if you haven't watched Harry Potter lately, that's where these names are coming from. But you can, so everything seems to be working out pretty good right now. But it seems like there's a couple names missing. What's probably the most important name that's missing right now in our hash table of names? Harry. So if you think about it, like here is the box for H, but notice Harry is not in this list yet. So if you look at a hash table, what we have right now is a collision. If we want to go ahead and put Harry in here, there's a couple options. One option we can do is you can just say, okay, this bucket is full, so let's just go ahead and put it here, even though that would be in the next bucket. So we have a collision. So what we can go ahead and do is move it down here, but then it would have the advantage of keeping everything kind of balanced. So if you needed to add something right there or another one, you can just go ahead and put it down here. So this idea where you just say, okay, this bucket is taken, go ahead and move it to the next one, that is known as linear probing. You're just looking for the next open spot. That is actually, it falls apart really quick, because then like what's happening if you're searching for Harry, that's fine. So like Harry would be here, but what would be another H name? Would be like Hagrid. But then Hagrid would be down here, and all of a sudden you can kind of see like things are getting pretty far away from where you are naturally looking. Like, okay, so Hermione's here, you're looking for Hagrid, you would have to jump all the way down here. So that's one way of dealing with the issue of collision, but it's not the way we're going to deal with it. What's another way that you might do? Or what's another thing that we might just end up doing? Anna, what do you think we could do? We could use a link or a linked list. And I think that's what the next slide does. Yeah. We essentially create a linked list. So, of course, that has some pros and cons, and you can see right here that we don't necessarily have order and things like that. The idea of us just doing a linked list, this is known as chaining. So briefly a moment ago, I explained the idea of linear probing. Right here, we're just going to use chaining as a way to solve this problem. So let's go ahead and look at what would happen. So you can see right here, if we had to go ahead and put Hagrid into that, we would end up with a little bit more of a linked list. And let's see, I think, yeah, I basically filled this out right here. So we have a bunch of linked lists, but if you think about this, what is the longest linked list right here we have? Say again? Is H, and how big is that linked list? Bailey? 3. So notice here the longest linked list is of length 3. How big would the linked list be if we weren't using this initial array as buckets to set up different linked lists? How long would it be? Anyone have a rough estimate? How would we find how long would the linked list be? It's just all of them, right? So it would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So again, if we did not use this initial array to essentially set up a bunch of buckets, we would have a linked list of 23. And you can imagine, like, if you were doing Harry Potter universe is fairly large. If you were to go ahead and just consider all of the muggles in that universe too, or something, I don't know, you'd end up with a fairly long linked list to go ahead and sort it, right? Or to go ahead and access, and then we already talked about the properties of linked list. So, how would we implement this? So just to maybe look at a brief implementation of a class, I'm just basically doing the init. We don't have any methods here. Like you actually, of course, could go ahead and define something that would be like insert, and then you would have to kind of think about the logic about how to go ahead and implement that. So again, just what's here is just the basic initializer. You can honestly Google Python hash table and get 5 different implementations of various functions, and I'll encourage you to maybe think about it a little bit. But let's think, what do we have to do when we initialize it? Well, you are given some initial size, and you're going to essentially create the table, and we're going to talk about that hashing. What does it mean to hash something here momentarily? But what we'll do is the hash table is, we just kind of abstracted that, encapsulated it into its own function. So if you remember this notation where we essentially are using like open bracket for some, again, this is, remember, just like a dummy variable. It's just a placeholder, so you don't really care. You're just going to create an empty list for whatever many times there are in range of size. So does anyone remember what this is called in Python? We're using a list. Does anyone? So it's called a list comprehension. Does that ring a bell? We spent like a half a day on it. I promise it is in the notes. I can find it. So this notation, again, if you want to brush it up, it's a nice Pythonic thing. This notation is using a list comprehension, but gotta spell here. So, but you could, what this is going to do, like for example, if self.size is, let's say, I don't know, let's do 3. What you would end up doing is essentially creating a list, and then you would have 3 empty lists right there. And then, of course, what the insert method would do is essentially find the appropriate list, that is the bucket, and then it would go ahead and insert the name into it. Of course, that's just using Python's list. You could also use the same linked list class we created a couple classes ago. I would encourage you to maybe play with the idea a little bit. But anyway, you could kind of see right here, there's the size, and then there's the tables. And again, that's just the initializer right there. So let's go ahead and actually talk about that hash. Why is it called a hash table? So if you think about it, each of those names, we got an input, and then we got some output, some sort of location that we're supposed to go ahead and put a certain element. So for example, we have a hash function that essentially took Albus, it went into the hash function, and then we got out 0. And I will maybe preface it, we're calling it a function, but remember, don't think about the mathematical function from calculus where each input has a unique output, because is that true here? If you were to plug in, let's say, well, no, I'm on base here. This is the same idea as a function. That's one of the properties of a good hash function, is that every time you plug in Albus for a function, it's going to give you 0. Now, again, you could have also what was another A name in Harry Potter? I don't remember. Do we have one? Not in our previous. Harry Potter. Any Harry Potter fans know another A name? Yeah, I'm stuck.
What's the name of the ghost in the girl's bath?
Agatha? I don't know. It just feels like a... no? I don't remember. Okay, I'll come back to that in a sec. But again, one of the properties of a good hash function is that you always know where it's going to go. It's not like Albus will sometimes go to 0 and Albus will other times go to 1. So it is the function that you do think about in calculus. But what is basically this? What is the function doing? How are you describing the output of all of these back here? So what is this function doing? It's simply, the input is the name, the output is the Lois? Okay, the output is the index where it belongs. So of course, if we were to plug in Albus. If we were to go ahead and hash Albus right there, that is going to give us 0. If we were going to hash Cedric, that is going to give us 2. So what is essentially this function doing? It's simply describe in words. What is this function doing? It's looking at the first letter and where it occurs in the alphabet, right? So this is one function. That this is not the only function right here, or the only hash function. Let me ask this question. Do you think this is a good hash function? How many say yes? This seems like a really good way to do it.
What are we trying to do?
It's a very general approach that if you're trying to put a name in here, you're going to go ahead and apply some hash function and it'll tell you where to put it. Of course, if there's a collision, you'll just go ahead and just tack on another list or another element to the end of the linked list. So just kind of looking at the way this is playing out, the hash function that's just looking at the first letter and assigning it to somewhere in the array based off of this first letter, is this seem to be looking like a good approach? You're saying yes. Why do you say yes?
Because it looks really good the way you've presented it so far.
Okay. Anyone want to say no? You want to say no?
Yeah.
Why do you want to say no?
It just seems like it could be done simpler.
Okay, looks like it'd be done simpler. This is a fairly simple hash function. So it's a really simple hash function. But what do you notice about the longest list there at 3?
They're not an alphabet.
So it's not in alphabetical order. So that might be something that, like, okay, is there some hash function that can consider the order? But is this balanced? Like, if you're looking at this, we have to go a long way here, but we haven't used these at all. So it's actually, let's see if I think that's the next slide right there. So Albus, Zacchaeus, yeah, hash functions. A good hash function has these characteristics. It's using only the data being hashed. So if we're thinking about just looking at the first letter and we're just looking at where it occurs in the index and where it occurs in the alphabet, is that by the first one, does our current hash function satisfy this? Yes or no? What do y'all say? Is it just using the name? I think so. Albus, it's not like it's pulling out his like hair color in the movie and using that. It's just using the name, so that's good. Is it using all of the data? Is it using the full name? No, so that's kind of disappointing. So that's maybe a vote against this current hash function. Is it deterministic? That is to say, every time you hash Albus, you'll get 0? Yeah, so that's be nice if the hash is a function still. So basically that's just saying it's a function. Is this hash function uniformly distributing data? Are the first letter of names uniformly distributed? I don't really know about the actual U.S. statistics there, but we had 3 H's. We had, I don't know, how many Q names do you know? Hubert? Quentin? How many Z names? Zacchaeus, Zacharias? You got to go back to your Bible to find the Z names. So if you think about this, it's not uniformly distributing the data. That there's going to be some parts of that hash table that are very long, and others that are basically empty. And does it generate different hash codes for does it generate very different hash codes for very similar data? So if you take think about 2 names. Let's say Harry and Hagrid. Kind of similar, they both start with H. Are those hashed very differently? No, they're hashed exactly the same. So there's an answer no, but why might you want it to be a very different hash code for a very similar piece of data? Go to this row again, Anna.
So that it's easier to find and differentiate between the similar data. So like when you find that index of H.
Okay, actually, but that's the opposite of what we want here. We want different hash codes for similar data. So
like all the H's. So like Hagrid and Harry would have very different.
Correct.
So that it's easier to find.
Okay, but they would be really far apart. One of the big applications of hash tables is for passwords. So it would be really like if you saw okay, if my password is password123, it's going to be hashed because we don't want to actually store that in a database for someone to steal. So hash123 should be not give the hacker any information if they're just 1 bit off. So that's kind of the idea of hashing, is that it's actually gonna really spread out the data that are very similar. So a lot of this is in security. It's a lot of hash tables. So anyway, I was just curious if anyone had maybe thought about that ahead of time, that how are they really storing your passwords? They better not be storing them as plain text. They should be doing, as Elizabeth talked about a little bit, as using some sort of cryptographic algorithm to hash it. So a lot of research goes into good hash functions. I took a course in security last semester. This is one of the most popular hash functions used today. It basically takes 80 keys and it runs over 80 rounds, and it essentially does a bunch of computation in each of the rounds, and then it goes ahead and ANDs the bits together. So it's very hard to figure out what the original data was, because it has very much been distorted using something known as a SHA-512 algorithm, so secure hashing algorithm. Anyway, we're not going to do that in this course. Just to make sure we understand that there are possible different hashing out functions, let's look at this function right here. And go ahead and take a moment and read through this, and maybe throw your mind back to a project from earlier in the semester. What is this hashing function doing? It's back to your Caesar project. So it's converting it to ASCII right here. So that's where it's looking at the order of it. And again, the 97 is essentially just shooting it back down to 0. So you could work with 0 through 26. So it's basically looking at each character, looking at where it occurs in the alphabet 0 through 25, adding it to the total, and then it is going to take the mod number of buckets. So just to do an example, I messed this one up. Ignore this right here. Let's try that again. So if you look at this, I realized this after I put this table in. Technically, everything should be like 0. That should be 1 because we're indexing at 0. So if I were to hash code using this hash function, what I would do is I would look at the C, and again, that should technically be 2. O should be 14, and then D should be 3. And Y should be 24. So let's see, what would that be? 26, 16, 43, right? So if I add these together, I get 3, carry 43. And then 43 mod the 10 is going to give you 3. So that just so again, this is only 10 buckets. So again, just to illustrate another hashing function, we have this one right here. So this one's a little bit better because it uses the entire string. Yeah, Anna.
Why did you mod?
Why did I mod 10? Just because I wanted to illustrate it. Doesn't have to be 26 buckets. This function has, there's a little typo here. That should be an int. So num buckets is a second argument that just says instead of 26 buckets, we're only using 10 buckets. So it was just to kind of make sure that you aren't stuck on the idea that it has to be 26. It could be 10, it could be 1,000. It all depends on how much you want to apply a rate. Okay, so let's go ahead and then talk about, so this one just adds another name right there. So you can see Lavender just has now made that one longer. And let's say, okay, here's the issue that we have with hash tables. The list keeps getting longer and longer. How can we fix that? What's something that we can do if we want a shorter linked list in each bucket? We can use a different hash function, right? So let's suppose we use a different hash function where instead of just looking at H, we looked at HA. Then if we kind of looked at we would of course need a larger array because we would have to go up, we would have to go down. But if we were to use all of the letters right there, how big is this array? It started with 26 buckets. If we wanted to use the first 2 letters of the name, how many buckets would you end up having to use? A little counting problem right here for those of you who have taken some probability. Not 26 to the 26, but
Where's the times? Where?
26 times 26. 26 squared. So notice if you were to adjust this scheme right here, we would end up with 26 squared. I think that's 676 buckets. So our array just got a lot bigger. But guess what? We now have solved the issue where Harry and Hermione are no longer in the same bucket. But Hagrid's so big. I mean, he's a giant. He's still in there with Harry. So what do? Do we go up to 3? Well, I already answered this. How many buckets would be required if we use the first 2 letters? Well, 26 squared. You would have 26 options for the first letter and then 26 options for the second. So if you realize that while this is making the linked list smaller, like to really get it really small, we'd have to use the first 3 letters. So that would be like this. And finally, when we use the first 3 letters, we have Harry, Hagrid, and Hermione all having their own bucket. And the question that I wanted to pose with this kind of idea of, is it a good idea just to make our array bigger? Well, will there be some buckets that are empty? Well, yeah. I don't know. Can you think of why? Because names are pretty much, have a certain pattern to them. You're going to have a lot of vowels in the second letter. You're really not going to have many Z's. Unless if you're in the Bible, then like as we talked about earlier, you have Zacchaeus, and he was a wee little lad. But yeah, why? It's just because names are not uniformly distributed. Anyway, that's just some thoughts about hash tables. The last thing we should mention about hash tables is their time complexities. So I put the word theoretical here. What is the theoretical time complexity of accessing? Let's suppose, so we have some key. The key is going to be like, we need to go for, let's suppose we need to find Hagrid. How long would it take us to find Hagrid? Could we do it in a constant number of steps? Or would it depend on how many names are in there? How many say it's going to depend on how many names? Okay, how many say it's to be constant? No one says constant. Let's just see. Anna, what do you say?
Well, you have to linearly go through the array, and then linearly go through the...
All right, well, you said one thing right. The other one is if it's access, you can actually go to the array in constant time because it's an array. So you have random access there. So you have big O of 1 plus big O of n, which of course is big O of n. So you have the random access, but then you still have the linear part from the linked list. What about inserting? Constant. And again, I mean, if you kind of think about this, we don't even have to worry about moving or copying the array because what we would do is we would do a linked list. So yeah, it's again going to be big O of n. And what about searching? Kind of the property of the linked list kind of takes over, right? So again, it's going to be big O of n because the search a linked list, you have to traverse the whole list, especially if it's not sorted in worst case. So the reason I put theoretically here though, is it kind of goes back to that conversation from earlier. Our longest linked list here is only going to be 3, but if we did a linked list by itself, it was going to be like 23. So that's why we say theoretically, because in practice, the big O is kind of like hiding a lot of those kind of like extra terms that aren't as a big deal because it's just looking at the big O. But let's see if we have a slide down there. We answered these right here. The accessing, the inserting, and the searching are all theoretically big O of n, but in practice, this is still much faster because the link list will be small. So it's actually in practice closer to constant time, especially if you have a good hashing function that distributes the data out over. If you had a good hashing function that equally distributes the data to a certain extent, it's still going to be faster. Like if you just based off of the number of buckets. 26, if you have a good hash function, is going to be 26 times faster than your just an array or just a linked list. So So mathematically, it's linear, but it's worth still noticing that in practice, this is a very good structure because you retain the random access from the array, and you still have the flexibility of using pointers to basically make sure that you don't have collisions in memory. Anyway, that is a hash table. Any questions? Yeah, Ken.
So this is more to do with the idea of like using a hash function as a password and stuff. So the idea is like, if you, with our example of Cody,
Okay.
that's not a one-to-one function because I could have a totally different password that would still come out with the answer of whatever it was, 10, right? So how would it know that your password is correct if you could have a different answer with the same hash?
So in practice, databases that are very large are using something known as salt values. So there's like a little extra value that is going to influence the actual hash function. Because you're thinking like this, I believe. You're saying, okay, what if my password was Cody and I hash this and it's going to give me some number, let's say it's going to give me like B73 pound exclamation point. And that's really what a hash is. Hash is going to work on the bits, and of course you could represent bits as ASCII and things like that. And then you're thinking like there would be hash, and if we hash Kenneth, what if it actually gave, the hash function gave the same one right here?
Yes.
So that's where things get a little bit more intricate in actual security, because they will consider some sort of salt value, which again is maybe using like part of the name to actually add some flavor or salt to it. So it's the idea of salting the hash function.
So so it's not possible to get the same value, or it is?
It makes it more difficult to where it's probabilistically almost, and again, these numbers are small, like hash functions. That was 512, so that's using 512 bits. So if you think
It's just not.
it's just probabilistically there's so many, and again, it's not, the way it's checking your password is this applying the same hash function and checking the actual, it's checking the, so like if you enter, like you were entering a password, if you typed in, so if I typed in Cody as my password, none of my passwords are Cody, don't try and log in and change your grades. What it's gonna do is gonna hash that B73 pound exclamation point. It'll compare this with what's in the database. So it actually doesn't even know, the database does not know my original password. It only compares hashes. So that's.
But the hashes are 512 bits long, is what you're saying?
Maybe even more at this point.
So yeah, the probability is
yeah.
the same. It's just basically 0.
Yes. And a good hash function is also going to distribute data very well, so it's things like that. So it's a very interesting subject that's a lot of really smart people have worked on. So, but make sure you still have a long password, because computers these days could really brute force most short passwords. So it's actually better to have a longer password than one with all those weird symbols, just throwing that out there. So.
Because it can run through.
Yeah, it could run through 8 to 10, even like whatever. If you throw an extra few symbols in, it's not a big deal. But if you have like a 20 to 25 symbolic password, it could be all letters, and the computer's still going to take a long time, because a good hash function is hiding the fact if it's numbers or letters and things like that. Anyway, really good, fascinating area research where there's an art to hash functions, as the way I've heard it described. So, if you remember, I still promise there's some sort of data structure that is like that. Constant time access, constant time lookup, constant time search, constant time insert, and that is known as a trie. Trie is short for retrieval. So let's go ahead and talk about a trie. By the way, if you ever want to make something faster, in computer science or in computers in general, what are we probably doing to the structure? If we're making it faster, if we want it to be faster, we probably are making it bigger. we have to store more information. So anytime, there's always this trade-off between speed and size. So a trie is going to be very large. Here's the basic idea right here. I just wanted to expose you what a trie node would look like. So it's going to store some letter, and that letter is going to store children, which are also other trie nodes. And then there's this other Boolean that says, hey, the word is finished or not. So let's go ahead and look at, there's 26 boxes there. And let's suppose that we want to go ahead and put Hagrid in this trie. So the way this is going to start is you're going to start with some array. And then what you'll do is you're going to put, so let's think about Hagrid. So the character, you're going to create a new trie node with a character that is H. You're going to initialize an empty list of children, and Hagrid is not the word, or H is not the word. So what we're going to do, and again, there's not necessarily the actual method there that will do it, but let's think about what we would do next. So we would maybe just look at the H is, again, the 7th letter in the alphabet, so that is in index 6 right here. So what you would do next is now look at A, and what you would do is create another array, and then you can go ahead and, well, it's actually, we just call it a list. So you can see right here, the children are right there. So if we were to look like the char was H, there's the children. So what we're going to go ahead and do is make a trie node. So that trie node will have all of that same information. We'll make another trie node right here for A, and we'll continue in this process. So you then make A is a trie node that has children, and it's going to have G. And you'll go ahead and then you'll have R, then you'll have I, then you'll have D. And then when you make the trie node here, that has the character of D. So this trie node with D is going to have basically the word finished is equal to true here, because we now know at this point in the structure, if you were to trace down these trie nodes with those characters, you will be able to spell the word Hagrid. So let's go ahead and say, what if we were to add another name to this? Let's say we wanted to add, I think Harry is what we do. So yeah, if you look at this, there's some overlap. These right here, both Harry and Hagrid both start with A. So if you're looking at the trie node here that has its children, you'll have one trie node that has the character G, and you'll have another trie node with the character R. But you can see right here, there's this idea that we don't have to create new structures completely for a different name. But if you look at this is a fairly big structure. And we're going to start getting to his access time. So to finish off Harry, you can see right here, this, of course, is going to branch off and do the R and the Y. So I think, Seth, you asked the question of, does a tree have to be binary? It does not. If you look at this tree, the root is up here. And if we were to completely fill this out with just millions of names, how many children would the first node have? It would have 26. It would have 26 children. And then again, each of those children would have another up to 26 children. Again, depending if you're doing it well, you aren't allocating memory until you need it. But again, this is an example of a 26 array tree that each node has 26 children. So let's go ahead and pose a question right here. Let me see where I posed it. I think that's the same slide right there. Oh, I'm adding Hermione. So you can see Hermione's over there. And again, indicated in green is the trie node with the word finish is equal to true. What is the height of this tree? So let's think about it specifically in this case. Just a quick review of height. What is the height of this tree? Anyone? Remember, the height of the tree is just how many steps down you are from the parent. So the root would be up here. So 1, 2, 3, 4, 5, 6, 7, 8. So again, the answer here is 8. The height is not too bad, right? what if, so in general, let's say we added 1 million names. What would the height of the tree be? It would be the longest name. So the height of the tree is simply going to be the longest name. So if the height of the tree is the longest name, and there were, let's say, 1 million names in here, does that affect the lookup time? Will the tree ever get larger than the longest name, or will you have to ever search through more than the longest name number of nodes? No. So what does that mean about the running times of these? Well, searching, it's going to be constant. It doesn't matter if the try has a 1 million elements in it, is because the longest searching you're going to have to do is the longest name. So that means the search is in big O of 1. And inserting, also big O of 1. Because all you may have to do is just initialize, maybe one or two more branches, pointers, and some extra try nodes. But the actual size of the try is already really big. If you look at that and you had a lot of names, there will be a lot of pointers, a lot of nodes. But the advantage of using something that large is going to be that searching and inserting are constant time. Yeah.
Okay, so just so I understand the concept a little bit, so it wouldn't be logarithmic because you're cutting off more than half when you decide like the first.
Okay, so keep in mind that all of this is relevant to some input. So n is the size of the try. So it doesn't matter if there's 10 names in the try or 1 million names in the try. It's just always going to be the same amount of time to look it up.
Because it's an array.
Because essentially let's say you were looking for, if you were looking for Herm. If you were looking for Herm, it doesn't matter that you don't have to all of a sudden essentially search through 1 million names if you're looking for Herm, because you would just trace this right down here and it would take the same amount. If you let's say you added another name, you wouldn't have to take longer to search for Herm.
Okay.
Because Herm is already in here.
Oh, so it's not dependent on, okay.
It's not dependent on how many names are in there. It's going to be constant time. Yeah. I think that's, all right. So in the last 2 minutes, let's look at abstract data types. And I'll give you, and then we're basically done with the content for the semester. Abstract data type is defined by its behavior or semantics from the point of view from the user. So if you think about all of these data structures we've looked at up to this point, we've been concerned about how they're implemented. Pointers moving around, allocating data in memory, where is it going to go? An abstract data type is essentially for the user to understand how it works. So there are two big abstract data types. One is called a queue. So the semantics of this one are enqueue and dequeue. A queue is exactly what you think about when you are waiting in line at a theme park. It uses the semantics is a first in, first out strategy. So you put something in, if you enqueue it, it's going to be in the front of the line. That should be the first one that comes out. This type of data structure is used a lot with like routing around the internet because basically these routers are trying to deal with millions of packets of data, and they want to say the ones that are in there first should be the ones sent on to the next router first. So that is indeed a queue. The other type of abstract data type that's pretty popular is a stack. When you stack something, do you grab from the bottom? Are you that risky? Like, I'm gonna stack a bunch of the plates and try to grab the bottom one out? It's not safe, right? It uses a semantic known as a LIFO, last in, first out. So if you stack one, you push onto a stack, then you could push on two, then you could push on three. But before you pop off 2 and 1, you have to pop off 3, and then you have to pop off 2, and then finally you could pop off 1. So this is, again, the semantics known as the stack. And of course, there's a video. Do you guys want to watch it before y'all leave? It looks interesting. So, well, here, the last one is a dictionary, which again, the semantics we're familiar with in Python as key values, and we have a way of dealing with it. Of course, is implemented using a hash table. So, there's data structures. So, do you guys want to watch this before you head on out? I think it's like 2 minutes. I mean, if you want to head on out, by all means, feel free. But it's a fun little video about stacks and queues. So,
Is this gonna be like posted?
of course. Okay. Yeah, you just won't get the laughter of your peers. I see how it is. So, all right. Okay, let's go ahead and load this up. All right, let me get the volume here. All right, do we have volume there yet? Did y'all hear anything? Oh, excuse me. Oh, there it goes.
Once upon a time, there was a guy named Jack. When it came to making friends, Jack did not have the knack. So Jack went to talk to the most popular guy he knew. He went up to Lou and asked, "What do I do?" Lou saw that his friend was really distressed. "Well," Lou began, "just look how you're dressed. Don't you have any clothes with a different look?" "Yes," said Jack, "I sure do. Come to my house and I'll show them to you." So they went off to Jack's, and Jack showed Lou the box, where he kept all his shirts and his pants and his socks. Lou said, "I see you have all your clothes in a pile. Why don't you wear some others once in a while?" Jack said, "Well, when I remove clothes and socks, I wash them and put them away in the box. Then comes the next morning, and up I hop. I go to the box and get my clothes off the top." Lou quickly realized the problem with Jack. He kept clothes, CDs, and books in a stack. When he reached for something to read or to wear, he chose a top book or underwear. Then when he was done, he would put it right back. Back it would go, on top of the stack. "I know the solution," said a triumphant Lou. "You need to learn to start using a queue." Lou took Jack's clothes and hung them in a closet, and when he had emptied the box, he just tossed it. Then he said, "Now Jack, at the end of the day, put your clothes on the left when you put them away. Then tomorrow morning, when you see the sun shine, get your clothes on the right, from the end of the line." "Don't you see," said Lou, "it will be so nice. You'll wear everything once before you wear something twice." And with everything in queues in his closet and shelf, Jack started to feel quite sure of himself, all thanks to Lou and his wonderful queue.
It's fun, right? All right, well, good job, everyone. If you have questions, feel free to stick around. Otherwise, I'll see y'all on Wednesday.